Good, thank you. So I'm really excited to give you a little overview on LOXO, the Lunar Occultation Explorer, which I hope will be the first dedicated astrophysics mission sent to the moon. We're waiting to hear about phase A selection any minute now, so we'll see how it goes. Next slide, please. So if you look at our current astrophysics fleet, it's quite varied, quite a diverse set of capabilities, science goals, but there is a gaping hole. For the past 30 years, development in nuclear astrophysics, or MEV gamma ray astronomy, I can switch with this? Okay. MEV gamma ray astronomy, nuclear astrophysics, has really been stale. Part of that is driven by the technical challenges, the costs, deployment strategies, and so that's something that we have sought to change with the development of LOXO. So this very short talk, I'm going to have to give you a brief overview of our motivations, our implementation and science goals, enough to be dangerous, but I'll be happy to answer any questions afterwards. LOXO is based on a technique that we've developed called the Lunar Occultation technique. As you'll see, the Lunar Occultation technique, the implementation is very low risk, it's highly scalable, so while we hope to be selected for the MidX Explorer, it has an opportunity to be reproposed, if we're not successful, for many other possible programmatic flight opportunities. It uses a high heritage implementation, which mitigates detector development, technology development, as you'll see. It leverages over 20 years of operational experience in the lunar environment, eliminates the use of complex kinematic reconstruction techniques and optics, and of course leverages the benefits of the lunar environment to achieve a sensitivity that cannot be achieved from Earth orbit. So it really represents a new paradigm for doing gamma ray astronomy. Maybe. There we go. The lunar occultation technique is embarrassingly simple, at least at its heart. Conceptually, what we're doing is we take data every 20 seconds or so, and we're looking for sources, gamma ray sources on the sky as they rise and set over the lunar limb relative to the orbiting detector. We've developed imaging and statistical framework methodologies to image those sources on the sky, and again, this eliminates the need for complex optics or kinematic reconstruction of events, enabling highly sensitive survey of the sky. So it's a classic on and off type of experiment with a bit of a twist. As we orbit the moon, we have a field of view that is determined solely by geometry, by the orbit altitude, and as we orbit the moon, we're constantly scanning the sky, looking for these sources as they rise and set over the limb, and I'll show you an example of this right now. This technique was validated in lunar orbit. Of course, we don't have LOXO yet, but we used the Lunar Prospector Gamma Ray Spectrometer, which orbited the moon in the late 90s for about a year and a half. And I repurposed that data to validate these techniques that I'm briefly describing to you now. And using that validation effort, we were able to, quote unquote, discover Cygnus X1, the first black hole candidate, using this technique. Cygnus X1 is not a discovery, it was well known, but this was the first high energy astrophysics performed from the moon and is a validation of this technique. So we feel comfortable moving forward. The downside is the Lunar Prospector Gamma Ray Spectrometer is really quite small, and so doing something like this again is not going to be sufficient to really break through and scan the cosmos. So what we've done, like any good piece of LOXO, we need a bagel. We've developed, our instrument is called the BGO Array for Gamma Ray Energy Logging. Yes, it's a bit of an effort to get that acronym. But bagel, we're not an imaging experiment, but we need a large instrument. So instead of building a monolithic instrument, we have an array of very modest gamma ray spectrometers that are not unlike the configuration of the lunar prospector gamma ray spectrometer. They're somewhat larger, some key differences, but they're all high heritage components, so there's very low risk. We can accommodate about 100 of these detectors, and in our full implementation, we have about 1.5 square meters of detector area. Our baseline instrument is about 7,500 square centimeters. The satellite bus is a custom bus that's built around the instrument, and this detector will be pointed to the nadir, pointed at the moon, and looking for sources as they rise and set over the lunar limb, as I described. The bottom line is the following. On the horizontal axis, you see energy. On the vertical axis is a measure of the sensitivity. The black curves are current or recently operating experiments, and you see the sensitivity of LOX. Depending on the energy range, we are almost 2 to 3 orders of magnitude more sensitive than previous instruments. And the dashed line there is E-astrogam, which is an experiment currently under consideration by ESA, which would cover some of the similar energy range, and you can see we do somewhat better than that as well. And all of this is because of the unique lunar environment where we have well-characterized background environment. It's not perfect. The moon is actually quite loud in gamma rays, but it's a relatively stable background environment, and so we can deal with those backgrounds quite effectively. Let me tell you briefly about our primary science motivation. We will do a full survey of the gamma ray sky, nuclear astrophysics, both broadband and nuclear lines, but our key science goal is the study of type 1a or thermonuclear supernova. Why are these important? Well, these are really the beacons of the cosmos. These are the lighthouses, if you will, that allow us to measure the shape and cosmic evolution history of our universe. And in 2010, these three gentlemen received a Nobel Prize by using type 1a supernova to identify the cosmic expansion, the acceleration of the cosmos. But since that time, we've entered an era of precision cosmology, and using these beacons of the cosmos, these thermonuclear supernova, we really need to understand them to a much higher degree. One of the assumptions they used is that all of these supernova are the same beast. They're the same kind of astrophysical event. And that turns out not really to be true. But we are going to observe these thermonuclear supernova in nuclear gamma rays, the fundamental emission from these objects that's driven by the conversion, the production of nickel-56 and the subsequent decay to iron-56. We're going to look at that fundamental emission and study the diversity of these objects. They are diverse. We're going to understand their progenitor systems. Are they the merging of two white dwarfs? Are they the accretion onto a white dwarf? We're going to study the nuclear propagation of the nuclear flame within the white dwarf itself and its destruction, and seek to understand the nucleosynthesis impacts of these diverse systems. The bottom line I want you to take away is the optical observations with which those gentlemen won the Nobel Prize, and people are currently doing supernova observations to understand the history of the universe. Those are very valuable. But the optical emission, while valuable, is secondary emission. It is reprocessed gamma rays. We're going to go after the gamma rays directly, which is going to tell us important details about the fundamental physics of these objects. This is an example. If you just concentrate on the box in the middle, these are simulated light curves to give you an idea of how we're going to do this science and get at the progenitor systems. Along the horizontal axis there, you see the time since these supernova exploded. The vertical axis is a measure of the number of gamma rays we detect. And what I want you to take away from this is that these light curves, the evolution, the nuclear evolution of these objects changes depending on what the progenitor properties are. And so we're going to be able to discriminate these by doing long-term monitoring over several hundred days of hundreds of these supernova. In fact, you see the gray dashed lines were the last sensitive gamma ray detectors. In fact, CompTel is the one I got my dissertation on. Didn't see very far. They didn't see very deep. With LOX, we can see out to about 150 megaparsecs, which means we're going to detect roughly 100 supernova, type 1a supernovas per year, which allows us to start doing population studies. Instead of detecting 1 or 2 or 3 thermonuclear supernova, in fact, there's only been one detected in gamma rays to date, and that was in 2014, we will detect hundreds, and so we can do these detailed population studies to really get after the diversity and related questions. So LOX was submitted last December for the 2016 MIDEX competition. As I mentioned, we're looking for phase A selection any second now. We have a set of very focused science goals, although we will really do many things. The science goals are focused on resolving the enigma of type 1a or thermonuclear supernova, understanding mass energy life cycle in the galaxy, and has a lot of synergy with WFIRST, NASA's, one of NASA's next large space-based telescopes, and LSST, one of NSF's large ground-based telescopes that's currently being built. We'll do all-sky monitoring and open up an era of gamma-ray astrophysics that hasn't existed for over 30 years. We have a very low-risk implementation. We're delivering hundreds of kilograms to lunar orbit for a MIDEX budget, which is quite nice. And one of the pieces I'm excited about, and I hope you're excited about too, that if we are selected, this will formally establish the moon as a platform for science beyond lunar and planetary science, which is quite a nice step in the right direction, if you ask me. And of course, sending a bagel to lunar orbit is always fun. All right, thank you.
Thank you, Rick.
Sure.
Yes, Doug, and then Jack. Watch out, here comes the cube.
Here, catch.
Do you get far enough back to see any of the expansion of the universe? Or
No.
is this only cataloging supernova?
Yeah, we only go to about 150 megaparsecs, so we're not technically seeing cosmological supernova. That is far, but it's not cosmologically far. Right. So what we're doing, those LSST and WFIRST, those are, or well, WFIRST is seeing the cosmological, the very distant redshift equal 1 supernova. What we're doing is really studying the physics of those supernova to understand how diverse are they, what is their dispersion and various properties that can be applied along with the observations of WFIRST to get at that precision cosmology. We won't do cosmology ourselves.
And will you be also doing the optics on those?
No.
Optical radiation?
No. And that's only a cost issue. I'd love to put an optical telescope on this, but nope.
Richard, very,
Yeah.
very impressive. This experiment has come a long way.
It has. Yeah.
And your science goals are equally impressive now.
Thanks.
Just a quick question about your orbit. Will you be
Yeah.
doing a polar precessing orbit?
Yeah.
What's
Yeah,
the
so I
parameters?
skipped over that. So we have a frozen orbit, periapsis about 750 kilometers, apoapsis about 1,100 kilometers.
Okay.
It's a frozen orbit relative to the moon, and the reason for that is to minimize the amount of resources we have to take with us to maintain the orbit. If we take less fuel with us, we can put available mass budget into the detector. This orbit, I think you're also in a frozen orbit. This orbit that we've identified is stable for way past the 3-year lifetime of this mission, so hopefully we can extend for longer if selected. But yeah, it's a frozen orbit. Yeah.
Any other questions? Yes, sir.
Yeah.
Maybe just a quick question. You already clarified what the physics for low redshift or
Yeah.
non-cosmological supernova versus the higher redshift ones. So what is the expectation in the diversity in terms of the physics,
Yeah.
in terms of redshift?
Yeah. That's a good question. So I can't we won't answer that directly. What I can tell you is the following, that and I'll answer this really quickly, one of the pieces of science we're going after is the following. There is a significant body of work that shows that the nature of these thermonuclear supernova is different depending on the kind of galaxy that hosts them. Their metallicity, the age metallicity of that galaxy, the morphology of the galaxy. And so in this local volume, this out to 150 megaparsecs, we'll be able to study that. The hope is that if we do identify multiple classes of these events, then WFIRST can pick out those classes and refine the systematics that are then applied to cosmology calculation, cosmology interpretation. So we can talk more offline.
All right.
Thanks.
Thank you very much. Very interesting talk. All right, so